Okay, welcome to Unit 5, Lesson 3, which is exploring how to find the angle between lines and planes in three-dimensional shapes. So the learning goals here are to find the angle between two lines and to find the angle between a line and a plane. So really this lesson is about applying trig strategies like SOHCAHTOA and the Pythagorean theorem to three-dimensional shapes. So one of the first things to be mindful of is how we can apply SOHCAHTOA to our three-dimensional shapes. So here's an example that kind of walks through the steps for you. So the first step is always to identify the right-angled triangle within the shape, which is what we did in the first two lessons. Then we can apply what we already know about trigonometry, so things like SOHCAHTOA and the Pythagorean theorem. So here's an example where you have a plane that's based on four vertices, so A, B, C, and D. That creates the flat plane. And you have a line. And the line is from vertex A to a point above the plane at G. So there's a line AG. And we're interested in the angle that that line makes with the plane. So when we think about the plane and we think about the angle, what we're looking for is when we start on the plane and we come up to the line of interest, that creates an angle called alpha. So we're interested in that angle. So we figure that out by drawing the lines that are necessary. So a perpendicular line from G to the plane. We're labeling where that perpendicular meets the plane, so that's point O. Then we draw our triangle and we label our angle alpha. And then we can use trig to find alpha. So the point where the perpendicular meets the plane, in this case, is point O, which is in the middle of the diagram. So a thing that's handy to note is that angle alpha is both considered to be an angle between the plane and the line, AG, but also considered to be the angle between two lines, OA and AG. So OA is a line that comes across the plane like this. So we can think of the angle either between the plane and AG or between AO and AG. So setting up these triangles is really important because if you don't set it up properly, when you try to apply your trig ratios, it won't work out the way you expect. So let's try some examples. So first we're just going to try some examples where all we're doing is identifying the angles. So we don't have to calculate anything yet, we just have to visualize where the angles will be. So we have some rectangular prisms here, and we're going to mark some angles on these diagrams. So the first one, question A, is looking for the angle that the plane ADHE, so we're going to shade in this plane here. We want the angle that this plane makes with the line AG. So we're going to draw in the line AG, and we're going to connect that down to H and back to A to create a triangle for ourselves. And that's going to be a right angled triangle. And the angle between the plane, which is the AH line, and the line of interest, which is AG, is going to be this angle right here. So that's the angle that they're describing in part A. Part B is also interested in the bottom plane, ADHE, except this time it wants the angle between that plane and between the line AC. So if we draw our line AC, we need to create a triangle for ourselves. So we're going to come down to D and back across to A. And the line between the plane, which is aligned with AD, and the line AC is going to be this angle here. So that's the angle of interest there. The third one now switches it up to look at the plane ABCD, which is the one on the side of the prism here. And we're interested in the angle that that plane makes with the line CE. So we're going to come down from C to E. We're going to make a triangle with the third vertex at D. So we're going to draw that along there. That's a right angled triangle. And the angle that CE makes with the plane part of which is CD, is actually going to be this angle up here. So we have the line and part of the plane, and that line comes out from that plane to make that angle theta. And the last one doesn't involve a plane at all. In fact, this time it's two lines. So the two lines are BH. So we're going to come down from B over to H, and HA. So we're going to join vertices H and A. And the third side of that triangle would be BA over here. And the angle of interest there is between the two lines that we drew to start. So there's your angle of interest. So again, in order to use trigonometric ratios accurately, you have to have an accurate triangle. So that's a really important part of what we're doing here. So similar skills can be applied to different shapes, like for example, pyramids. So here are some other examples with pyramids. So in the first example, we're looking at the base ABCD and the angle that that base makes with the edge DE. So DE comes up from the corner to the apex of the pyramid, and we can come down to the center and back out to D to make a right angle triangle. And the angle between the base and the edge of DE is going to be this one here. And the second one, you're looking for the angle between the base or the plane ABCD and the line ME, where M is a midpoint here between C and D. So if we connect that midpoint to the apex, we can generate a triangle here. And the angle between the plane and the line ME is going to be this angle here. The third one is looking at two lines. So the line BE, which goes down the back of the pyramid, and ED, which comes through the front. So once we have two lines, it's very clear where the third edge of the triangle is going to be. And the angle is going to be between the first two lines. So it's going to come up here in between our two sides. And the last one is looking at DE and EC. So those are along this face here. We can join up the triangle there, and the angle between the lines is going to be the one at the top. So that's how you can sort of visualize the triangles inside a three-dimensional shape. And once you can find the triangle, the math is math you've done before, SOHCAHTOA and Pythagorean theorem. So let's try some examples where we actually have some dimensions that we can work with. So here's the first example, a rectangular prism where you know some dimensions. AE is 9 centimeters, AB is 2 centimeters, and EH is 5 centimeters. So we have a length of 9, a width of 5, and a height of 2. So the first thing we're interested in is the angle, the plane ADHE. So again, that's the bottom plane here. We want the angle that that plane makes with AG. So we're going to draw AG here. And we're going to create a triangle by coming back down to the plane and across. And that's a right angle triangle. So this is okay. We do know that GH is going to be the same as AB. So that'll be 2 centimeters. However, we don't know AH. And we're trying to find AG, or we need one of those other sides to be able to find the angle. The angle we're looking for is between the plane and AG, so that's what we need. But we need at least two sides of the triangle to find the angle. So sometimes you have to look for another triangle that can help you out. So for example, I see that if I come across the length of the base and up the width of the base, I create another triangle, AEH. And I already know AE and EH, so I can use that triangle to find AH for myself. So again, I'm just going to, like I did in previous lessons, I'm just going to give myself a quick little diagram here. AE is 9 centimeters, EH is 5 centimeters. So Pythagorean theorem again, AH squared, the hypotenuse, is going to be 9 squared plus 5 squared. So that'll be 81 plus 25, which is 106, which means that AH is the square root of 106 centimeters. Now I'm going to leave that as an exact answer because it'll help me be more precise and accurate in my second step. So that found me AH. So now I can go back to the original triangle of interest, which is AGH. I know GH is 2 centimeters, and now I know that AH is root 106. And now I can use all of this to find my angle. So I have the angle, I have the opposite side across from the angle, and I have the adjacent side. So that's a classic case for the tan ratio. So tan theta is opposite, which is 2 over root 106, which means that theta is equal to, I'm going to do 2 divided by the square root of 106, and then I have to do the tan inverse of that ratio. And that's going to give me to 3 sig figs approximately an angle of 11 degrees. So this one was a bit of a two-stepper. I had to find a second triangle to allow me to get a piece of information I needed to really solve the problem I was after. So let's try the second part. So the second part doesn't involve a plane at all. It involves 2 lines. So BH, which comes down across here, and HE, which comes across here. And then we can complete the triangle by going from E to B. Now, it may not look like it, but these actually are perpendicular to each other. So they meet at a right angle. And again, it's kind of a similar situation to question A. I know that the base of this triangle is 5, or one leg of this triangle is 5, but I don't know either of the other 2 sides. However, I can see another little triangle here on the front face of the prism. So in that triangle, I see B, A, and E. And that's a right angle triangle where I know BA is 2 centimeters and AE is 9 centimeters. So if I'm interested in finding BE, which will help me with the ultimate goal here, then I can use the Pythagorean theorem. So 2 squared plus 9 squared. So BE squared is 85, which means BE is the root of 85 centimeters. Now that I know BE, I can go back to my original triangle. So I'm just going to reorient it a little bit. So I have B, I come down to E, and I go across to H. And there's a right angle at BE. EH is 5 centimeters, and BE is root 85 centimeters. And the angle I'm looking for is between BH and HE. So it's this angle down here in the corner, which is the same as this angle here in my triangle. So again, I have an unknown angle, I have the opposite side, and I have the adjacent side. So tan theta is root 85 divided by 5. So theta is root 85 divided by 5. And I do the tan inverse of that ratio, and I get approximately 61.5 degrees. So again, bit of a two-stepper, but it works out in the end. So let's try one more. We did a rectangular prism here. We'll do another shape with flat faces, so this time we'll work with a pyramid. So here's our pyramid of interest, and we know a couple things about this pyramid. The base is rectangular, so the dimensions of the base are 6 centimeters by 4 centimeters, and our height of the pyramid is 7. So the first order of business is to calculate angle AEO. So what helps me here is to actually draw the triangle. So I have AEO, which is this triangle here. That is a right angle because the height and the base are perpendicular. And I'm interested in this angle up here, which is at E. So what I'm going to do is I'm going to identify what I know already. I know the height is 7 centimeters. Again, I don't know AE and I don't know AO. So I kind of have to look around and say, okay, which of those sides could I find? AE is going to be pretty tricky, but AO is part of the base, and I do know some information about the base. For example, there's a diagonal that cuts across the base like this, and that's part of a bigger triangle, which is like half the base. And I know that AO is going to be exactly halfway along this diagonal. So if I think about this triangle here along the base, I have A, C, and D. I have AD of 6 centimeters and CD of 4 centimeters. So AC squared is going to be 6 squared plus 4 squared, which is 36 plus 16, which is 52. So AC is root 52 centimeters. Therefore, from this, I know it must be true that AO, which is halfway across, is going to be root 52 over 2. I got to split that in half. So now that I know that information, it's really handy because I can use that to figure out my ultimate goal here. So my other triangle is the one I originally drew, which is AEO. And now I know 7 centimeters, but I also know AO is root 52 over 2. And I'm looking for this angle at the top. So I have the angle, I have the opposite side, and I have the adjacent side. So tan of theta is root 52 divided by 2, all over 7. So theta, if I take root 52, divide that by 2, take that answer divided by 7, and do the tan inverse of that ratio. So my theta is approximately 27.3 degrees when I round to 3 sig figs. So the next part is to consider triangle AEC. So in this one, I'm going to highlight EC, AE, and I'm going to go across here like that. So what's interesting here is that all I'm doing by creating triangle AEC is I'm mirroring AEO with the triangle CEO. And so what that actually does is it doubles up this angle at the top. So the interesting thing is AEC, which is the angle that spans all the way across the top of this yellow triangle, is actually just double the angle AEO, because I've literally just like doubled that triangle by flipping it around to the other side of the pyramid. So I can just take this 27.3 degrees here, and I can double it. So angle AEC is going to be approximately 54.5 degrees. So that's kind of nice. I didn't actually need to do any other trig. I just used the idea that I have two mirror image triangles, like back to back, so they're going to have the same angles. Okay, so on to part B. And part B is asking us to find angle EMO. So M is this midpoint here. So I'm going to mark it on my diagram, and I'm going to create that triangle. E to M, and over to O, and then back to E. So that's a right angle triangle. And the nice thing is I do know a lot about this triangle already. So if I give myself a little sketch here, I have E, O, and M. I know OM is going to be half of the base length here, which means OM is going to be 3 centimeters. And EO, I already know, is the height, is 7 centimeters, and the angle I'm interested in is the one at M. So this angle here, which is here on my triangle. So this one's easy, no additional work required. I have an unknown angle, I have the opposite and adjacent sides. So tan theta is 7 over 3, which means that theta is going to be about 66.8 degrees. Okay, so that one wasn't so bad. Now we're just on to the last part, which is part C. So part C is looking for the length of ED. So ED goes down there, we come down to EO, and we come back across to D with a right angled triangle. And the nice thing is OD is actually going to be the same as AO, because if you think about coming across this diagonal, which is AC, which we found in part A, the two diagonals are actually going to be the same. So OD is also going to be root 52 over 2, which is the same as AO. So if we draw this little triangle here, we have O, D, and E. So we have 7 centimeters, and we have root 52 over 2. And our angle of interest is, oh no, we're looking for the length of ED. Okay, so if we're looking for a length, we have two sides already. It's a right angled triangle, so it's a case for the Pythagorean theorem. So ED squared is going to be 7 squared plus root 52 over 2 squared. So that's 49 plus root 52 divided by 2 and then squared. That gives us 13. So ED squared is 62, which means ED is root 62 centimeters. And again, I'm going to leave that as an exact answer because it'll make it more accurate later on. So there's the length of ED. That's part I. Part II is to find angle DEC. So now I'm looking at the triangle that goes from D to E to C. So this one in green here. So that one, what do I know about this triangle? I know the vertices, D, E, and C. I know DC is 4 centimeters. And I know ED is root 62. Now, this is going to be an isosceles triangle. So the diagonal on this side will be the same as the diagonal on this side. So I can mark that also as root 62. Now, the angle I'm going for here is DEC. So I'm looking for the angle at the top here. And when I know all three sides, it's important to remember that this one is not a right angled triangle. So I know three sides, it's not a right angled triangle, which means this is a case for the cosine law. So cos of theta is going to be root 62 squared plus root 62 squared minus 4 squared over 2 times root 62 times root 62. So theta is going to be, root 62 squared is obviously 62, so I'm going to do 62 plus 62. I'm going to subtract 16, and root 62 on the bottom times root 62 is 62, so I'm going to divide that by 2 times 62. So that's my ratio, and then I have to take this time the cos inverse of that ratio because I'm using the cosine law, and I get theta is approximately equal to 29.4 degrees. So there are some applications of trig skills like Pythagorean theorem, SOHCAHTOA, and the cosine law to triangles within 3D shapes. So hopefully you can keep practicing with the homework, and then we'll move on to the next lesson.